This video is audio content only. It does not contain any video footage or images. If you are expecting visual content, please be aware. This is intentionally provided in an audio-only format. We recommend listening to the audio rather than watching the screen. Thank you for your understanding. Welcome! Have you ever looked up at the night sky and wondered just how far away those stars really are? Today, we're exploring one of astronomy's greatest challenges, measuring the vast distances across space. From nearby planets to the edges of the observable universe, we'll discover the ingenious methods astronomers have developed to map the cosmos. Whether you're curious about parallax, standard candles, or redshift, this journey will reveal how we've learned to measure the seemingly immeasurable. Let's begin our voyage through space and time. Chapter 1. Measuring the size of Earth and defining the astronomical unit. Before astronomers could reach out to measure the vast distances between stars and galaxies, they first had to solve a more immediate puzzle. How large is the world beneath our feet, and how far away is the sun that warms it? These questions, which might seem straightforward today, challenged humanity's greatest minds for millennia. The answers they eventually found became the essential foundation upon which all cosmic distance measurements rest. Without accurately knowing Earth's dimensions and its separation from the sun, the entire enterprise of mapping the universe would collapse like a house built on sand. The story begins in ancient Greece, where scholars armed with nothing more than geometry, careful observation, and brilliant reasoning accomplished something remarkable. They measured the size of Earth with surprising accuracy, using methods so elegant that they still inspire wonder today. The most famous of these measurements was performed by Eratosthenes of Cyrene around 240 BCE. Eratosthenes served as the chief librarian at the Great Library of Alexandria, and his method relied on a simple observation. At noon on the summer solstice, the sun shone directly down a well in the Egyptian city of Syene, meaning the sun stood precisely at the zenith. Yet on that same day and time in Alexandria, several hundred kilometers to the north, the sun cast a measurable shadow. Eratosthenes reasoned that if Earth were flat, the sun would appear at the same angle everywhere at the same moment. The existence of different shadow angles could mean only one thing: Earth's surface must be curved. By measuring the angle of the shadow in Alexandria, which turned out to be about 7 degrees, and knowing the distance between Alexandria and Syene, he could calculate Earth's circumference using straightforward geometry. His reasoning went like this. If 7 degrees of arc along Earth's surface corresponded to the distance between the two cities, then 360 degrees, a full circle, must correspond to Earth's complete circumference. The distance between the cities was known from the records of professional pacers who measured roads for the Egyptian government. Eratosthenes arrived at a figure equivalent to about 40,000 kilometers for Earth's circumference, remarkably close to the modern value of just over 40,000 kilometers. This achievement demonstrates something profound about the nature of scientific measurement. The ancient Greeks possessed no satellites, no lasers, no electronic instruments, yet through careful observation and logical reasoning, they determined the size of their world with impressive accuracy. This same spirit of using fundamental principles to bootstrap our way to knowledge characterizes all subsequent efforts to measure cosmic distances. Understanding Earth's size proved essential for the next great challenge, determining the distance to the sun. This measurement would ultimately define the astronomical unit, the fundamental yardstick against which all distances within the solar system would be measured. But finding this distance presented a far more difficult problem than measuring Earth's circumference. Unlike the distance between two cities on Earth's surface, which ancient travelers could pace out directly, the chasm separating Earth from the sun could not be measured by any straightforward means. The sun sits too far away for simple triangulation using baselines on Earth's surface to yield precise results. For centuries, astronomers struggled with this problem. They could observe the planets moving across the sky and developed increasingly sophisticated models to predict their motions. Johannes Kepler's laws of planetary motion, formulated in the early 17th century, revealed beautiful mathematical relationships between a planet's orbital period and the size of its orbit. These laws meant that once you knew the precise distance to any one planet, you could calculate all the others. Kepler's third law states that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This relationship provides exact ratios between planetary orbits, but gives no absolute scale. It's rather like having a map that shows the relative positions of cities, but includes no scale bar to tell you how to convert the map distances into actual kilometers or miles. To establish the absolute scale of the solar system, astronomers needed to measure the actual distance to at least one solar system body. The Sun itself presented difficulties because its edges appear fuzzy and indistinct, making precise positional measurements challenging. Instead, astronomers turned their attention to Venus, the bright planet whose orbit lies between Earth and the Sun. The key lay in a rare celestial event, the transit of Venus across the Sun's face. During such a transit, Venus appears as a small black dot slowly crossing the solar disk, and the exact timing of the transit depends on the observer's position on Earth. Astronomers realized that by observing a Venus transit from widely separated locations and carefully timing when Venus appeared to enter and leave the Sun's disk, they could use parallax, the apparent shift in position due to changed vantage point, to calculate Venus's distance. Combined with Kepler's laws, which gave the ratio of Venus's orbit to Earth's orbit, this would yield the Earth-Sun distance. The challenge was that Venus transits occur in pairs separated by 8 years, with more than a century between pairs. The transits of 1691 and 1699 had been predicted but poorly observed. The scientific community prepared intensively for the next pair, scheduled for 1761 and 1769. These observations would require unprecedented international cooperation and would test the limits of 18th century technology and human endurance. The 1761 transit inspired one of the first truly global scientific campaigns. Astronomers from multiple nations traveled to far-flung corners of Earth to position themselves for optimal observations. Some journeyed to Siberia, others to southern Africa, still others to the islands of the Pacific. The observations faced numerous obstacles. Weather proved uncooperative at many sites. Political tensions complicated matters. The 7 Years' War raged during the 1761 transit, yet French and British scientists sometimes collaborated despite their nations being enemies. The phenomenon known as the black drop effect, where Venus seemed to remain connected to the Sun's edge by a dark ligament even after apparently detaching, made it difficult to determine the exact moment of contact. The 1769 transit generated even more ambitious expeditions. Captain James Cook sailed to Tahiti to observe the event, combining scientific observation with exploration. Other observers stationed themselves from Hudson Bay to Norway to India. The French astronomer Guillaume Le Gentil suffered one of science's most unfortunate series of mishaps. He traveled to India for the 1761 transit, but found himself aboard a ship at sea on the crucial day when the weather and the ship's motion made observation impossible. Determined not to fail twice, he remained in the region for 8 years, waiting for the 1769 transit. When the day finally arrived, clouds covered the Sun at the critical moment. He returned to France after 11 years to discover he had been declared legally dead and his estate distributed to his relatives. Despite these difficulties, the combined observations from both transits allowed astronomers to calculate the Earth-Sun distance. Various analyses of the data yielded values clustering around 150 million kilometers, though the scatter remained large by modern standards. These measurements established the first reasonably accurate value for the astronomical unit, confirming that the Sun lies vastly farther from Earth than anyone in previous centuries had imagined. The scale of the solar system suddenly expanded in humanity's understanding, and with it came a new perspective on our place in the cosmos. The astronomical unit, once established through these heroic observational campaigns, became the fundamental ruler for measuring distances within the solar system. Astronomers expressed planetary distances in astronomical units rather than kilometers, because the relative distances determined from orbital dynamics were more precise than the absolute distance measurements. Even today, though we know the astronomical unit in kilometers to extraordinary precision, astronomers often find it more intuitive to think in terms of AUs when discussing solar system distances. The 20th century brought revolutionary improvements to distance measurement through the development of radar. Radio waves travel at the speed of light, a precisely known constant. By bouncing radar signals off planets and measuring the round-trip travel time, astronomers could determine distances with exquisite precision. Radar astronomy began in earnest in the 1960s, when powerful transmitters sent microwave pulses toward Venus and successfully detected the faint return echoes. These radar ranging measurements provided distance determinations far more accurate than anything achievable through optical observations of transits. Modern radar measurements of Venus and other nearby planets have allowed astronomers to determine Earth's orbital dimensions to an absolute precision of a few meters and a relative precision of a few parts in 100 billion. These measurements refined and superseded the transit observations. Today, tracking of interplanetary spacecraft as they journey through the solar system provides another means of verifying these distances. As spacecraft coast through interplanetary space, ground-based tracking stations monitor their positions by measuring radio signal travel times, continuously improving our knowledge of solar system dimensions. In 1969, the Apollo 11 mission placed retroreflectors on the lunar surface, opening another avenue for precision distance measurement. Lunar laser ranging experiments fire short laser pulses from Earth-based observatories toward these retroreflectors and detect the reflected pulses. By precisely timing the round trip, astronomers can measure the Earth-Moon distance to an accuracy of 1 to 2 centimeters. This technique has provided not only extraordinarily precise measurements of the lunar orbit, but also stringent tests of gravitational theory. The consistency between lunar laser ranging results and other distance measurements confirms the reliability of our cosmic measuring system. The International Astronomical Union eventually adopted an exact definition for the astronomical unit: 149,597,870.7 kilometers. This definition reflects our current best understanding of Earth's mean distance from the Sun. Note that this is defined as a specific number of kilometers rather than being measured from the actual Earth-Sun separation, which varies slightly as Earth follows its elliptical orbit. The astronomical unit represents the semi-major axis of Earth's orbit, essentially the average of the maximum and minimum distances during Earth's year-long journey around the Sun. Understanding Earth's size and its distance from the Sun represented humanity's first steps in measuring the cosmos. From Eratosthenes' shadow measurements in ancient Alexandria to the heroic Venus transit expeditions of the 18th century, and finally to modern radar and laser ranging achieving precision of meters or centimeters, these efforts establish the fundamental scale of our solar system. The astronomical unit, painstakingly determined across millennia of observation and calculation, provides the essential foundation upon which astronomers would build increasingly sophisticated methods for reaching beyond the solar system to measure the distances to stars and galaxies. Chapter 2. Trigonometric Parallax. Direct geometric distance measurements to nearby stars. Once astronomers had accurately measured the astronomical unit, they possessed a powerful new tool for reaching beyond the solar system. The same principle that allowed ancient surveyors to map distant mountains and that enabled astronomers to measure Venus's distance during transits could now be applied to the stars themselves. This technique, known as trigonometric parallax, would prove to be astronomy's first reliable method for determining stellar distances, and it remains the most direct and trustworthy measurement technique available today. The concept behind parallax is simple enough that you can demonstrate it right now. Hold your thumb at arm's length and look at it with only your left eye open. Now close your left eye and open your right. Your thumb appears to jump sideways relative to the distant background. This apparent shift happens because your two eyes view your thumb from slightly different positions. The closer an object is to your face, the larger the apparent shift. If you bring your thumb much closer, the shift becomes so large that it's almost impossible to fuse the two images. This same principle of viewing an object from two different positions forms the basis for measuring stellar distances. For astronomical applications, astronomers replace your two eyes with two positions of Earth in its orbit around the Sun. They photograph a nearby star once, then wait 6 months until Earth has moved to the opposite side of its orbit and photograph the same star again. If the star is relatively close, it will appear to have shifted position slightly against the much more distant background stars, which appear fixed because they lie so far away that their parallax shifts remain unmeasurable. The size of this shift, called the parallax angle, relates directly to the star's distance through simple geometry. Imagine drawing a long, thin triangle with the Sun at the apex, Earth at one corner of the base, and the nearby star at the other corner. The distance from Earth to the Sun, 1 astronomical unit, forms one side of the triangle's base. The distance from the Sun to the star forms one of the long sides. The parallax angle sits at the star's position, between the line from the star to Earth and the line from the star to the Sun. For the vast majority of stars, this angle is extraordinarily small because stars sit tremendously far away compared to Earth's orbital size. Even the nearest star beyond the Sun produces a parallax angle less than 1 arcsecond, and most stars have parallax angles measured in tiny fractions of an arcsecond. To put this in perspective, 1 arcsecond represents 1/3600th of a single degree. If you were to look at a dime from a distance of 2 kilometers, the angle it would subtend in your vision equals about 1 arcsecond. The nearest bright star, Alpha Centauri, sitting more than 4 light-years away, shifts by only about 3/4 of an arcsecond as Earth swings from one side of its orbit to the other. Measuring such minuscule angles taxes the limits of what telescopes can achieve, even with modern technology. This explains why detecting stellar parallax eluded astronomers for so long. The ancient Greeks understood the principle of parallax and attempted to measure it for stars. Their failure to detect any parallax led some Greek astronomers to conclude, correctly, that the stars must lie at enormous distances. Others, however, used this null result to argue that Earth could not possibly be moving around the Sun, for if it were, the stars should show parallax. This reasoning contributed to the geocentric model's long dominance. Not until the 16th and 17th centuries, when Copernicus and Galileo revived the heliocentric model, did the search for stellar parallax take on renewed urgency. If Earth truly orbited the Sun, stellar parallax had to exist. Finding it would provide direct proof of Earth's motion. Many astronomers tried and failed throughout the 17th and 18th centuries. The problem was that they underestimated the distances to stars by vast factors. Even in the early 19th century, many astronomers thought the nearest stars might lie only a few astronomical units away, perhaps 10 or 20 times the Earth-Sun distance. At such distances, parallax angles should have been easily measurable with existing telescopes. The persistent failure to detect parallax increasingly suggested that the true distances must be far larger than anyone had imagined. The breakthrough finally came in the 1830s, when several factors converged. Telescopes had improved to the point where they could measure stellar positions to better than 1 arcsecond accuracy. Astronomers had learned to focus their efforts on stars most likely to be nearby, such as stars with large proper motions, stars that appeared to drift slowly across the sky relative to background stars, suggesting proximity. And perhaps most importantly, several talented observers possessed both the skill and determination to pursue the most painstaking precision measurements. 3 astronomers working independently achieved nearly simultaneous success in measuring stellar parallax in the late 1830s. Friedrich Wilhelm Bessel in Germany focused on a faint star in the constellation Cygnus, catalogued as 61 Cygni. This star had been known since the previous century to have the largest proper motion of any star then observed, moving more than 5 arcseconds per year across the sky. Bessel reasoned that such rapid apparent motion likely indicated a nearby star. Using a specialized instrument called a heliometer mounted on a telescope at Königsberg Observatory, Bessel made hundreds of painstaking measurements over more than a year, carefully comparing 61 Cygni's position to 2 much fainter background stars visible in the same field of view. In 1838, Bessel announced his result. 61 Cygni showed an annual parallax of about 0.29 arcseconds. This tiny angle, barely 1/3 of an arcsecond, implied a distance of about 11 light-years, or more than 600,000 times the Earth-Sun distance. For the first time in history, humanity had measured the distance to a star. Bessel's achievement demonstrated that the stars lay vastly farther away than anyone had seriously considered. The universe had suddenly become immensely larger than the small cosmos of earlier imagination. Almost simultaneously, Friedrich Struve in Russia measured the parallax of Vega, the bright star in Lyra, and Thomas Henderson at the Cape of Good Hope measured Alpha Centauri, the nearest bright star to our solar system and visible only from southern latitudes. Henderson actually made his observations of Alpha Centauri before Bessel measured 61 Cygni, but Henderson hesitated to publish, doubting his own results because they seemed to imply such enormous distances. By the time Henderson finally published in 1839, Bessel had already announced his 61 Cygni results and earned the credit for the first stellar parallax measurement. Henderson's measurements of Alpha Centauri proved the more important in the long run, however, because Alpha Centauri turned out to be the nearest star system to the Sun, lying just over 4 light-years away with a parallax of about 3/4 of an arcsecond, the largest stellar parallax observable from Earth. The success of these first parallax measurements vindicated Copernicus and Galileo, confirming that Earth indeed orbits the Sun. More importantly, parallax provided astronomers with their first reliable, direct method for measuring cosmic distances. Unlike methods that would be developed later, parallax measurements require no assumptions about the physical nature of the object being observed. You need not know anything about what kind of star you are measuring, what it is made of, how bright it truly is, or how it produces its energy. Parallax is purely geometric. You measure an angle, you know the baseline, Earth's orbital diameter, and you calculate the distance through straightforward trigonometry. This independence from astrophysical modeling makes parallax the gold standard against which all other distance measurement techniques must ultimately be calibrated. The relationship between parallax angle and distance takes such a simple form that it inspired astronomers to define a new unit of distance specifically for parallax work. The parsec, a name formed by combining parallax and arcsecond, represents the distance at which a star would show a parallax angle of exactly 1 arcsecond. At this distance, the 1 astronomical unit baseline of Earth's orbit would subtend an angle of 1 arcsecond as seen from the star. No real star lies this close. Even Proxima Centauri, the very nearest star, sits about 1.3 parsecs away. But the parsec provides a convenient unit because distance in parsecs equals simply 1 divided by the parallax angle in arcseconds. A star with a parallax of 1/2 arcsecond lies 2 parsecs away. A star with a parallax of 1/10 arcsecond sits 10 parsecs distant. This inverse relationship makes calculations refreshingly straightforward. 1 parsec equals approximately 3.26 light-years, or about 206,000 astronomical units, or roughly 30 trillion kilometers. While the parsec might seem like an arbitrarily defined unit, it arose naturally from the geometry of parallax measurements and has become the preferred distance unit among professional astronomers. Science writing aimed at the public often uses light years because this unit has intuitive appeal. It represents the distance light travels in 1 year. But research papers nearly always express distances in parsecs and its larger relatives, the kiloparsec, 1,000 parsecs, and megaparsec, 1,000,000 parsecs. The examples of the nearest stars illustrate how parallax works in practice. Proxima Centauri, a faint red dwarf star in the constellation Centaurus, visible only from southern latitudes, has a parallax of 0.768 arcseconds. Applying the parallax formula gives a distance of 1.30 parsecs, or 4.24 light years. Alpha Centauri, actually a system of 3 stars, including Proxima as the third and faintest member, has the 2 brighter components at nearly identical distances of about 1.3 parsecs. Sirius, the brightest star in Earth's night sky, shows a parallax of 0.38 arcseconds, placing it at 2.6 parsecs, or roughly 8.6 light years. Barnard's star, a faint red dwarf noted for having the second largest proper motion of any star, lies at 1.8 parsecs. Even though dozens of star systems have now been catalogued within 10 parsecs of the Sun, these examples make clear that the nearest stars lie at enormous distances compared to solar system scales. Despite the triumph of Bessel, Struve, and Henderson, measuring parallaxes remained extraordinarily difficult throughout the 19th and most of the 20th century. Even with improving telescopes and techniques, Earth's atmosphere presented a fundamental limit. Atmospheric turbulence causes stars to twinkle and their positions to blur, preventing ground-based measurements from achieving precision better than a few hundredths of an arcsecond, even under ideal conditions. This atmospheric limit meant that reliable parallax measurements from the ground reached only about 50 to 100 parsecs, a small fraction of our Milky Way galaxy's 30,000 parsec diameter. To reach farther and measure fainter, more distant stars, astronomers would need to escape Earth's atmosphere altogether. The revolution came with the European Space Agency's Hipparcos satellite, launched in 1989. The name Hipparcos honored both the ancient Greek astronomer Hipparchus and also formed an acronym for High Precision Parallax Collecting Satellite. Operating for 4 years from space, Hipparcos measured the parallaxes of more than 100,000 stars, with precision as good as 0.001 arcseconds, about 1 milliarcsecond. Additional measurements of lower precision extended to more than 1,000,000 stars. To put this precision in perspective, 1 milliarcsecond equals roughly the angle subtended by a golf ball viewed from across the Atlantic Ocean. At this precision, parallax measurements became reliable out to distances of several hundred parsecs, allowing astronomers to map a substantial volume of space around the Sun and accurately calibrate other distance measurement techniques. Before Hipparcos, astronomers had reliable parallax measurements for fewer than 1,000 stars, accumulated painstakingly over more than a century. Hipparcos increased this number 100-fold practically overnight, providing the first 3-dimensional map of the solar neighborhood and revolutionizing our understanding of stellar populations, the structure of the Milky Way, and the calibration of the cosmic distance ladder. The nearest stars could now have their distances determined with uncertainties of only about 0.2 or 0.3%. A precision sufficient for testing theoretical models of stellar structure and evolution. The success of Hipparcos motivated an even more ambitious mission. The European Space Agency's Gaia satellite, launched in 2013, carries more advanced instruments capable of measuring stellar positions to an accuracy of tens of microarcseconds for the brightest stars. 1 microarcsecond equals 1/1,000,000th of an arcsecond, or about the angular size of a human hair viewed from 1,000 kilometers away. Gaia is surveying more than 1 billion stars, mapping not only their positions and parallaxes, but also their motions, brightnesses, and colors. Its parallax measurements extend reliably to several thousand parsecs, approaching the distance to the Milky Way's center. Gaia data releases have provided parallaxes for stars throughout much of our galaxy, creating an unprecedented three-dimensional map of stellar positions. These space missions demonstrate that technology continually pushes the boundaries of what parallax measurements can achieve. Yet fundamental limits remain. Even with perfect instruments in space, parallax can only measure distances to the nearer stars within our own galaxy. The parallax angles for more distant stars become vanishingly small, eventually dropping below even the most precise measurements that future technology might achieve. For stars in other galaxies, parallax angles become millions or billions of times too small to detect. This limitation means that parallax alone cannot map the universe. To reach beyond our galactic neighborhood, astronomers must turn to other techniques. Nevertheless, parallax holds a privileged position in the hierarchy of cosmic distance measurements. It provides the only direct, geometric, model-independent measurement of stellar distances. Every other technique for measuring distances to astronomical objects must eventually be calibrated using parallax measurements of nearby examples. When astronomers want to measure the distance to a remote galaxy, they might observe certain types of variable stars in that galaxy, whose intrinsic brightness they have determined. But how do they know the intrinsic brightness? By observing nearby examples of the same type of star and measuring their distances through parallax. Then using the known distance and observed brightness to calculate the true luminosity. This chain of inference connects even the most distant cosmic objects back to the fundamental parallax measurements of our nearest stellar neighbors. The journey from Bessel's first measurement of 61 Cygni to Gaia's mapping of 1 billion stars spans nearly 2 centuries and exemplifies astronomy's character as a cumulative science. Each generation of astronomers builds upon the work of those who came before, achieving what earlier generations could only imagine. The trigonometric parallax method, conceived in ancient Greece, attempted unsuccessfully for centuries, first achieved in 1838 and perfected in space-based observatories in the 21st century, now provides humanity with reliable distance measurements throughout a substantial volume of our galaxy, establishing the geometric foundation upon which our understanding of the cosmos is built. Chapter 3: Cepheid Variables and the Cosmic Lighthouse. Even as Hipparchus and later Gaia revolutionized parallax measurements, extending reliable geometric distances to thousands of parsecs, these triumphs only emphasized how much farther astronomers needed to reach. Our Milky Way galaxy stretches approximately 30,000 parsecs from edge to edge, and the nearest large galaxy, Andromeda, sits more than 700,000 parsecs away. The overwhelming majority of the universe lies beyond parallax's reach, no matter how precise the measurements become. To measure distances to other galaxies and probe the structure of the cosmos, astronomers required a fundamentally different approach, one that could bridge the vast gulf between the nearest stars and the distant galaxies. The solution emerged from an unexpected direction: stars that change their brightness. Throughout history, observers had noted that a few stars did not shine with steady light, but instead varied in brightness over time. Some of these variations occurred because one star passed in front of another in a binary system, temporarily blocking some light. But others varied for reasons intrinsic to the stars themselves. These intrinsically variable stars, though initially considered mere curiosities, would ultimately provide the key to measuring cosmic distances far beyond the reach of parallax. Among the most important class of variable stars are the Cepheids, named after their prototype Delta Cepheid, a moderately bright star in the northern constellation Cepheus. Delta Cepheid drew serious attention in the late 18th century when astronomers noticed its brightness varying regularly with a period of about 5.4 days. The star would brighten rapidly, reaching maximum luminosity, then fade more slowly back to minimum before brightening again. This pattern repeated with clockwork regularity, cycle after cycle, year after year. The distinctive sawtooth shape of its light curve, the graph showing brightness changing over time, made Cepheids unmistakable once astronomers learned to recognize them. Other variable stars showing similar behavior were soon discovered, each with its own characteristic period ranging from about 1 day to several months. These stars earned classification as Cepheid variables, and astronomers cataloged them wherever they appeared in the sky. Yet for decades, no one understood why these stars varied, and no one suspected that they held the secret to measuring the universe's vast distances. That discovery awaited the work of a quiet, determined woman working at Harvard College Observatory at the turn of the 20th century. Henrietta Swan Leavitt joined Harvard Observatory in 1893 as a volunteer among a group of women known as the Harvard Computers. The observatory's director, Edward Charles Pickering, had hired these women to perform the painstaking work of examining thousands of photographic plates of the night sky, measuring stellar brightnesses, and cataloging positions. The work required extreme care and patience, but offered little recognition and meager pay when pay was offered at all. Leavitt, who had studied astronomy and earned credits toward a graduate degree at what would become Radcliffe College, initially worked without compensation. Even after she began receiving wages, she earned only 30 cents per hour, or $10.50 per week. She worked alongside other talented women computers, including Annie Jump Cannon, who, like Leavitt, was deaf. Pickering assigned Leavitt to study variable stars in the Magellanic Clouds, 2 fuzzy patches of light visible from the southern hemisphere. These clouds, later recognized as small companion galaxies orbiting our Milky Way, contained thousands of stars close enough together that they could be photographed on the same photographic plates. This proximity made them ideal for comparing relative brightnesses. Importantly, all the stars in each Magellanic Cloud lie at essentially the same distance from Earth, give or take a small percentage. This fact, though not fully appreciated at the time, proved crucial for Leavitt's discovery. Working methodically through the photographic plates, Leavitt identified variable stars one by one. By 1908, she had cataloged 1,777 variables in the Magellanic Clouds, a remarkable achievement in itself. But Leavitt did more than merely count variables. She measured their brightness variations and determined their periods. Then she noticed something extraordinary. The Cepheid variables with longer periods appeared brighter on average than those with shorter periods. This was not obvious at first, because the relationship held only for variables within the same cloud, and the pattern was obscured by the variable's brightness fluctuations and by measurement uncertainties. By 1912, Leavitt had refined her measurements and focused on 25 Cepheid variables in the small Magellanic Cloud whose periods and brightnesses she could determine with confidence. She plotted their average apparent brightness, how bright they appeared from Earth, against the logarithm of their periods, and found a clear, tight correlation. The relationship appeared nearly linear. Longer period Cepheids were systematically brighter than shorter period ones. The paper announcing this result, communicated through Pickering but prepared by Leavitt, would transform astronomy. Leavitt wrote simply that a straight line could readily be drawn through the points, showing that there was a simple relation between the brightness of these variables and their periods. Here was the key insight. If all these Cepheids lay at essentially the same distance, then differences in their apparent brightness reflected genuine differences in their intrinsic luminosity, their absolute magnitude, or true power output measured from a standard distance. The period luminosity relation meant that by measuring a Cepheid's period, which could be determined simply by watching how quickly it varied, an astronomer could infer its absolute magnitude. These distance determinations work because Cepheids serve as standard candles, astronomical objects whose intrinsic brightness can be determined, allowing distance to be calculated from their apparent brightness. Compare that known luminosity to the star's observed apparent brightness, and distance follows directly from the inverse square law of light. Brightness decreases with the square of distance. If you know a star's true luminosity and measure how bright it appears, the ratio between them reveals how far away it must be. Leavitt understood that her discovery provided a potential method for determining distances, but she needed one more piece of information, the actual distance to at least one Cepheid, which would establish the 0 point of the relation and convert relative brightnesses into absolute luminosities. She wrote that if the distances to these stars could be determined, their absolute magnitudes would establish the relation between period and actual luminosity. The Magellanic Clouds themselves provided an early test. If you assumed a distance to the Small Magellanic Cloud, you could calibrate the Cepheid period luminosity relation. Then, observing Cepheids in the Large Magellanic Cloud and measuring their periods and apparent brightnesses would reveal the distance to the large cloud. Modern measurements place the Large Magellanic Cloud at about 50 kiloparsecs and the Small Magellanic Cloud at about 60 kiloparsecs, roughly 160,000 and 200,000 light-years respectively. The period luminosity relation's true power emerged when astronomers began finding Cepheids in other galaxies. In 1923, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory in California to resolve individual stars in several spiral nebulae, including the Great Nebula in Andromeda. The nature of these spiral nebulae had been debated for decades. Were they clouds of gas within our Milky Way, or were they enormous independent stellar systems lying far outside our galaxy? Among the stars Hubble resolved, he identified Cepheid variables. By measuring their periods and applying Leavitt's period luminosity relation with the best available calibration, Hubble calculated distances of several 100,000 parsecs for these nebula. This result finally settled the debate. Spiral nebulae were not clouds within our galaxy, but rather vast, distant galaxies themselves. The universe abruptly became vastly larger in human understanding. Hubble's initial measurement placed Andromeda at about 285 kiloparsecs, though modern measurements using improved calibrations yield 770 kiloparsecs, or roughly 2.5 million light-years, a dramatic revision illustrating the challenges of proper calibration. Hubble's achievement demonstrated that Cepheids could serve as cosmic lighthouses, visible across intergalactic space, and carrying within their regular pulsations the information needed to measure their distances. This capability depends on Cepheids being intrinsically very luminous stars. Classical Cepheids are core helium-burning stars that evolved from B-type or late O-type main sequence stars. They shine with luminosities around 1,000 times the Sun's output, with radii roughly 50 times solar. Such tremendous luminosity makes them visible across millions of light-years, detectable in relatively nearby galaxies even with modest telescopes, and spectacularly conspicuous when observed with powerful instruments. The story of Cepheid distance measurements took a dramatic turn in the 1950s when Walter Baade made a critical discovery that would revolutionize the cosmic distance scale. Baade realized that astronomers had been observing two distinct types of Cepheid variables without recognizing the difference. Classical Cepheids, the kind Leavitt had studied in the Magellanic Clouds and Hubble had observed in Andromeda, are relatively young, massive population 1 stars found in the disks of spiral galaxies where star formation continues. But a separate class, Type 2 Cepheids, includes older, lower-mass population 2 stars found in globular clusters and galactic halos. These two populations follow different period luminosity relations because their different masses and compositions affect their pulsation properties. Early calibrations of the period luminosity relation had inadvertently mixed the two types of Cepheids, using nearby Type 2 Cepheids and globular clusters to calibrate the relation that was then applied to the more luminous population 1 Cepheids in distant galaxies. This confusion led to systematic underestimates of extragalactic distances by approximately a factor of 2. When Baade corrected this error, the implications were staggering. The size and age of the universe abruptly doubled. Galaxies that had seemed relatively nearby were suddenly revealed to be twice as distant. This correction exemplifies how critical proper calibration of standard candles proves to be. A subtle systematic error propagated through the entire cosmic distance ladder, fundamentally altering our understanding of the universe's scale. Understanding why Cepheids pulsate required advances in stellar astrophysics that came decades after Leavitt's discovery. Stars exist in a delicate balance between gravity pulling inward and pressure pushing outward. For most stars, this balance remains stable over long periods. But in certain regions of stellar parameter space, specific combinations of mass, radius, temperature, and composition, stars become unstable to pulsations. Cepheids occupy what astronomers call the instability strip in the Hertzsprung-Russell diagram, a graphical representation plotting stellar luminosity against surface temperature. The pulsation mechanism that drives Cepheid variability involves a natural feedback loop acting as a heat engine in the star's atmosphere. Deep within the star's outer layers lies a zone where helium transitions from singly ionized to doubly ionized. When this ionization zone compresses, its opacity increases dramatically, meaning it becomes more effective at blocking radiation trying to escape from the star's interior. The trapped radiation builds up pressure and heats the zone, which lifts the overlying atmospheric layers and causes the star to expand. As expansion proceeds, the gas does work against gravity and cools. Eventually, the temperature drops enough that doubly ionized helium recombines to singly ionized helium. The zone's opacity then decreases, allowing trapped radiation to escape. With pressure support removed, the atmosphere falls back inward, compressing again, and the cycle repeats. This alternating trapping and releasing of energy drives the observed periodic changes in the star's radius, temperature, and luminosity. The pulsation period depends fundamentally on the star's internal structure, essentially on its average density. More massive, more luminous Cepheids have larger radii and lower average densities, causing them to pulsate more slowly. This physical connection between the pulsation period and the star's fundamental properties gives rise to the observed period-luminosity relation. The boundaries of the instability strip define where Cepheid pulsations can occur. Only in the narrow temperature range where the helium ionization zone sits at the right depth can stars pulse as Cepheids, explaining why these useful objects remain relatively rare. Modern formulations of the Cepheid period-luminosity relation include corrections beyond the simple period-luminosity law. Metallicity, the abundance of elements heavier than helium in a star's atmosphere, affects the relation slightly because it changes atmospheric opacity. Different theoretical and empirical studies have led to a range of conclusions, and the effect of metallicity on the observed properties of Cepheids remains an active area of research. Astronomers also account for color, measuring Cepheid brightness in multiple wavelength bands to correct for reddening caused by interstellar dust lying between the Cepheid and Earth. By observing Cepheids through multiple filters and measuring their colors, astronomers can estimate and correct for this extinction. Infrared observations prove particularly valuable because dust affects infrared light much less than visible light. Additional complications arise when observing Cepheids in distant galaxies. Crowding becomes serious. At large distances, individual stars blur together even in sharp images. Superior telescope resolution has largely overcome this problem for relatively nearby galaxies, allowing reliable Cepheid measurements throughout the local universe. Cepheids remain detectable with current instruments out to about 30 megaparsecs, roughly 100 million light-years. This reach extends well beyond our local group of galaxies, encompassing the Virgo cluster and numerous other galaxy groups and clusters. Within this volume, Cepheids serve as the primary method for measuring distances to galaxies. Henrietta Leavitt never received recognition commensurate with her discovery during her lifetime. She continued working at Harvard Observatory, cataloging variables and pursuing other astronomical projects, but her contributions went largely unrecognized outside the astronomical community. In 1924, the Swedish mathematician Gösta Mittag-Leffler wrote to nominate her for the Nobel Prize, only to learn that she had died of cancer in 1921 at age 53. The Nobel Prize cannot be awarded posthumously. Yet Leavitt's legacy endures in every distance measurement that uses her period-luminosity relation, in every map of the universe's structure built on Cepheid observations, and in the expanded cosmic perspective her work helped create. From Leavitt's patient examination of photographic plates at Harvard to modern observations pushing the frontiers of precision, Cepheid variables have established themselves as one of astronomy's most valuable tools. Their regular pulsations provide a cosmic clock that reveals not time but distance. The period-luminosity relation stands as one of astronomy's most important discoveries, transforming stars that merely twinkled into beacons that illuminate the scale of the universe. Building on geometric measurements that reveal distances to nearby stars, Cepheids extend our cosmic reach by more than 1,000-fold, from a few thousand parsecs to tens of megaparsecs, from our galactic neighborhood to the realm of other galaxies. This bridge between the local and the extragalactic represents an essential middle rung on the cosmic distance ladder, connecting the solid geometric foundation to the vast scales of cosmology. Chapter 4. Type A Supernovae as Standardizable Cosmological Candles. Even with Cepheid variables providing reliable distance measurements out to about 30 megaparsecs, astronomers confronted a humbling reality. This reach, impressive as it was, barely scratched the surface of the observable universe. The cosmos extends for thousands of megaparsecs in every direction, filled with billions of galaxies whose distances Cepheid would never measure. These distant galaxies lie so far away that even the most luminous Cepheid variables appear far too faint for even the most powerful telescopes to detect and study. To probe the universe's large-scale structure, to measure its expansion rate across cosmic history, and to understand its ultimate fate, astronomers needed distance indicators vastly more luminous than any star that varies on a timescale of days or weeks. They needed objects bright enough to be seen across billions of light years, objects that could serve as beacons visible from one side of the universe to the other. The answer came from the most violent stellar explosions known to astronomy, supernovae. The term supernova, meaning new star in Latin, reflects the historical observation that these events occasionally cause stars to appear suddenly in locations where no star had been visible before. Ancient astronomers recorded such appearances, interpreting them as the birth of new celestial objects. Modern understanding reveals the opposite. Supernovae mark not birth, but death, the catastrophic destruction of stars in explosions so powerful they briefly outshine entire galaxies. A single supernova can radiate more energy in a few weeks than our Sun will emit over its entire 10 billion-year lifetime. This extraordinary luminosity makes supernovae visible across cosmic distances that would render ordinary stars utterly invisible. Supernovae are rare events in any given galaxy. In a typical large galaxy like our Milky Way, supernovae occur perhaps once or twice per century on average. This rarity explains why, despite their spectacular brightness, only a handful of supernovae have been recorded in our galaxy throughout human history. The supernova of 1064, observed by Chinese astronomers and producing the Crab Nebula, and the supernova of 1604, studied by Johannes Kepler, stand among the most famous. For more than 3 centuries after Kepler's supernova, no supernova appeared in our galaxy within reach of telescopes, though many were eventually discovered in other galaxies as observers learned to systematically search the sky. This scarcity meant that to find supernovae regularly and study them in detail, astronomers needed to survey thousands of galaxies continuously, waiting patiently for these rare explosions to announce themselves by suddenly brightening. The discovery that not all supernovae are alike proved crucial for their use as distance indicators. Astronomers eventually classified supernovae into distinct types based on their spectra and light curves. Type 2 supernovae show prominent hydrogen lines in their spectra and result from the core collapse of massive stars that have exhausted their nuclear fuel. These explosions vary considerably in their peak brightness depending on the mass of the progenitor star and the details of the explosion mechanism, making them poor candidates for standard candles. Type 1b and Type 1c supernovae also result from core collapse, but in stars that have lost their outer hydrogen envelopes before exploding, and they too show significant variation in peak luminosity. Type Ia supernovae stand apart from these core collapse varieties. Their spectra show strong silicon absorption lines but no hydrogen, and their light curves follow a remarkably consistent pattern. They brighten rapidly to maximum light, reaching approximately the same peak luminosity regardless of which galaxy they inhabit, then fade gradually over weeks and months in a characteristic pattern. This uniformity suggested that Type Ia supernovae arise from a fundamentally different and more regular process than core collapse supernovae, and indeed this proved to be the case. The story of understanding Type A supernovae begins with a brilliant young physicist crossing the Indian Ocean by ship in 1930. Subramanian Chandrasekhara, just 19 years old, had completed his undergraduate studies at the University of Madras in India and had won a scholarship to pursue graduate work at Cambridge University in England. The voyage from India to Europe in those days required 3 weeks aboard a steamship, and Chandrasekhara, never one to waste time, spent the journey working on a problem in stellar structure that had captured his attention: the ultimate fate of stars. By 1930, astronomers understood that when stars like our Sun exhaust their nuclear fuel, they eventually settle into a stable configuration called a white dwarf. These compact stellar remnants, roughly the size of Earth but containing the mass of the Sun, glow dimly from residual heat but generate no new energy. The Danish physicist Wilhelm Anderson and the English physicist Ralph Fowler had shown that white dwarfs are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. This pressure, unlike ordinary thermal pressure, does not depend on temperature and can support a cold, dead star indefinitely. Chandrasekhar revisited the equations describing white dwarf structure during his ocean voyage, applying both quantum mechanics and special relativity to understand how these objects behave. His calculations led to a disturbing conclusion. As a white dwarf's mass increases, it must contract to higher densities to generate enough degeneracy pressure to support itself. But special relativity places limits on how fast particles can move, and at sufficiently high densities, electrons approach these relativistic limits. When Chandrasekhar worked through the mathematics carefully, he discovered that electron degeneracy pressure could not support a white dwarf above a certain critical mass. Beyond this threshold, which he calculated to be approximately 1.4 times the Sun's mass, no known force could prevent gravitational collapse. This result, now known as the Chandrasekhar limit in his honor, means that white dwarfs have a maximum possible mass. Chandrasekhar presented his findings to the Royal Astronomical Society soon after arriving in England, where they met with skepticism from some prominent British astronomers who found the implications unsettling. If white dwarfs could not exist above the Chandrasekhar limit, what happened to stars that tried to exceed this threshold? The answer remained unclear for years, but decades later, astronomers realized that Chandrasekhar's limit held the key to understanding Type A supernovae. A white dwarf in isolation, sitting peacefully in space, will remain stable forever, provided its mass stays below the Chandrasekhar limit. But many stars exist in binary systems with close companions. If a white dwarf orbits another star and the two orbit closely enough, the white dwarf's intense gravity can pull matter from the companion star's outer layers. This stolen material spirals onto the white dwarf surface, gradually increasing its mass. Alternatively, if the companion is itself a white dwarf, the two might eventually spiral together and merge, suddenly creating a single object whose combined mass exceeds the limit. In either scenario, when the white dwarf approaches the critical mass of approximately 1.4 solar masses, it faces a crisis. As the mass rises toward the Chandrasekhar limit, the white dwarf compresses under its own gravity, heating its interior. White dwarfs are composed primarily of carbon and oxygen, the ashes of helium fusion from the star's earlier life. Under the extreme pressures and temperatures in a white dwarf approaching the mass limit, this carbon and oxygen can ignite in a runaway thermonuclear reaction. Unlike ordinary nuclear burning in stars, which is regulated by a feedback mechanism that prevents runaway, the degenerate matter in a white dwarf provides no such safety valve. The nuclear reactions accelerate, converting carbon and oxygen into heavier elements through fusion reactions that release tremendous energy. Within seconds, the entire white dwarf detonates. The resulting explosion tears the star apart completely, leaving no remnant. The energy released in the explosion rivals the combined energy output of all the stars in a galaxy, causing the supernova to briefly shine as brightly as 100 billion suns. The explosion ejects debris at speeds of 10,000 to 20,000 kilometers per second, hurling the star's ashes into surrounding space. Among these ashes are substantial quantities of radioactive nickel-56, created during the peak of the thermonuclear runaway. The radioactive decay of nickel-56 to cobalt-56 and then to stable iron-56 powers the supernova's light curve, causing it to glow brightly for weeks after the initial explosion. This radioactive decay process proceeds at a fixed rate determined by nuclear physics, contributing to the uniformity of Type A supernova light curves. The crucial point for distance measurement is that all Type A supernovae explode at approximately the same mass, the Chandrasekhar limit, because this represents the threshold where white dwarfs become unstable. Exploding at the same mass means releasing approximately the same amount of nuclear energy, producing approximately the same amount of radioactive nickel, and consequently achieving approximately the same peak luminosity. This uniformity makes Type A supernovae extraordinarily valuable for measuring cosmic distances. In practice, Type A supernovae are not perfectly standard. Individual explosions show variations in peak brightness of about 30 to 40%. However, astronomers discovered that these variations correlate strongly with the light curve shape. Intrinsically brighter Type A supernovae fade more slowly after maximum light, while fainter ones fade more quickly. This relationship allows observers to standardize Type A supernovae empirically. By measuring the light curve shape, quantified through parameters like the decline rate or the stretch factor, astronomers can correct the observed peak brightness to what it would have been for a standard template, bringing the scatter in luminosity down to only about 10 to 15%. With this standardization, well-observed Type A supernovae yield distance measurements with typical uncertainties around 7 to 10% per object, competitive with or better than Cepheid distances. The exceptional luminosity of Type A supernovae, combined with their standardizable brightness, allows them to be detected and studied at enormous distances. Modern surveys routinely find Type A supernovae in galaxies more than 1,000 megaparsecs away, well over 100 times farther than the maximum range of Cepheid observations. The most distant Type A supernovae discovered to date lie more than 3,000 megaparsecs distant, so far that we observe them as they appeared more than 10 billion years ago when the universe was less than a quarter of its present age. At such distances, Type A supernovae provide not merely distance measurements, but rather probes of cosmic history, revealing how the universe has expanded over most of its lifetime. The power of Type A supernovae to trace cosmic expansion became spectacularly apparent in the late 1990s. Two independent research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to measure distant Type A supernovae with the goal of determining how the universe's expansion rate has changed over time. Gravity attracts all matter to all other matter, so astronomers expected that the universe's expansion should be gradually slowing down, decelerated by the gravitational pull of its matter content. The question was how much the expansion had slowed. To answer this required finding supernovae at high redshift, measuring their distances through their light curves, and comparing those distances to what would be expected if the expansion rate had remained constant or had decelerated. Finding distant supernovae required systematically surveying large areas of sky, comparing images taken weeks apart to identify the sudden appearance of new point sources of light in distant galaxies. Following up these discoveries to obtain detailed light curves and spectra demanded intensive telescope time on the world's largest observatories. Both teams invested years in developing efficient search techniques and building the necessary infrastructure. In 1998, the teams independently announced shocking results. Distant Type 1a supernovae appeared fainter than expected, by 10 to 15% compared to predictions based on a universe decelerating under its own gravity. Fainter apparent brightness meant greater distance, implying that the universe had expanded more than expected between the time the supernova light was emitted and the present day. Instead of slowing down, the expansion of the universe was speeding up. This acceleration contradicted all conventional expectations and demanded a dramatic revision of cosmological theory. The implications were profound. Some form of energy must pervade space, creating a repulsive effect that overcomes gravity's attractive pull on cosmic scales. This energy, dubbed dark energy because it neither emits nor absorbs light, apparently accounts for approximately 70% of the universe's total energy content, yet had somehow escaped detection until revealed by distant supernovae. The discovery transformed cosmology, introducing a mysterious new component that dominates the universe's evolution, yet whose nature remains enigmatic. For this discovery, Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics. The supernova evidence for cosmic acceleration rests fundamentally on accurate distance measurements, which in turn depend on proper calibration of the Type A supernova luminosity scale. This calibration requires observing Type A supernova in galaxies whose distances are known through Cepheid variables. Systematic errors in Cepheid distances propagate directly into systematic errors in the Type A calibration, which then affect all cosmological conclusions drawn from distant supernovae. Modern supernova surveys have found and studied thousands of Type A supernovae at distances ranging from our cosmic backyard to the early universe. These observations constrain not only the present expansion rate, but also how that rate has changed over cosmic history, encoding information about the balance between matter, radiation, and dark energy at different epochs. Combined with other cosmological observations, including measurements of the cosmic microwave background radiation and the distribution of galaxies across space, Type A supernovae have helped establish the standard model of cosmology, which describes a universe dominated by dark energy and dark matter, with ordinary matter comprising less than 5% of the total. The success of Type A supernovae as cosmological distance indicators has motivated intensive efforts to understand them in ever greater detail. Observers work to identify and correct subtle systematic effects. Does dust in distant galaxies extinguish supernova light differently than dust nearby? Have the properties of Type A supernovae evolved over cosmic time as the chemical composition of stars has changed? Could gravitational lensing by foreground mass concentrations magnify or demagnify distant supernovae, biasing distance measurements? Addressing these questions requires large samples of well-observed supernovae, sophisticated statistical analyses, and continuous refinement of theoretical models describing how white dwarfs explode. From Chandrasekhar's calculations aboard a ship crossing the Indian Ocean to modern surveys detecting supernovae when the universe was young, Type A supernovae have evolved from mysterious stellar explosions to precision cosmological tools. Their exceptional luminosity allows them to be detected across billions of light years, making them indispensable for measuring cosmic expansion. In doing so, they revealed not only distances, but also the accelerating expansion of space itself, demonstrating once again that the tools we develop to measure the universe often surprise us by revealing phenomena we never suspected existed. Chapter 5. Universal Expansion and Redshift. Even as Type A supernovae push distance measurements out to thousands of megaparsecs, revealing the accelerating expansion of the universe, they still could not reach the most distant objects that powerful telescopes could detect. At the farthest edges of the observable universe lie galaxies and quasars so remote that even the brilliant explosion of a Type A supernova would appear impossibly faint. To measure the distances to these most remote objects, to map the universe's structure across its entire observable expanse, astronomers needed a fundamentally different approach, one that could work where all other methods failed. The solution emerged from one of the most profound discoveries in the history of science: the realization that the universe itself is expanding, carrying galaxies away from each other, and that this expansion leaves a measurable imprint on the light traveling across cosmic distances. The story begins not with distance measurements, but with spectroscopy, the technique of splitting light into its component wavelengths to reveal the spectrum of colors and dark absorption lines that characterize each source. By the early 20th century, astronomers had learned to interpret stellar spectra, recognizing that specific patterns of dark lines indicated particular chemical elements in a star's atmosphere. Hydrogen produces a characteristic series of lines at precise wavelengths, as do helium, calcium, iron, and all other elements. These spectral fingerprints allowed astronomers to determine what distant stars were made of without ever touching them. Vesto Slipher, an American astronomer working at Lowell Observatory in Arizona in the early 1900s, began obtaining spectra of the faint, fuzzy patches of light known as spiral nebula. To Slipher's surprise, the spectra of spiral nebula showed familiar absorption lines produced by stars, but these lines did not appear at their normal wavelengths. Instead, the entire pattern of lines appeared shifted toward either the blue or the red end of the spectrum. Most remarkably, some of these shifts were enormous by the standards of stellar spectroscopy, far larger than the shifts produced by stars moving within our galaxy. Slipher interpreted these shifts correctly as Doppler effects, the same phenomenon that makes an ambulance siren sound higher-pitched as it approaches and lower-pitched as it recedes. When a light source moves toward an observer, its waves compress, shifting the spectrum toward shorter, bluer wavelengths. When a source moves away, its waves stretch, shifting the spectrum toward longer, redder wavelengths. The magnitudes of the shift Slipher measured implied that many spiral nebula were rushing away from us at speeds of hundreds or even thousands of kilometers per second. By the early 1920s, he had measured radial velocities for more than 40 spiral nebula, finding that the vast majority showed redshifts, meaning they were moving away from us. Only a few nearby nebula showed blue shifts indicating approach. The meaning of these recession velocities became clear only when combined with distance measurements. In 1927, the Belgian priest and physicist Georges Lemaitre analyzed the relationship between galaxy distances and velocities, proposing that the universe itself was expanding. His work, published in the Belgian journal, went largely unnoticed. 2 years later, Edwin Hubble independently discovered the same relationship. By combining Slipher's velocity measurements with distance measurements to several galaxies, Hubble found a clear trend. More distant galaxies receded faster than nearby ones. In 1929, Hubble published a simple plot showing the recession velocities of galaxies against their distances. Despite the scatter in the data, a straight line could be drawn through the points, indicating a direct proportionality between distance and recession velocity. This relationship, expressed mathematically as velocity equals h0 times distance, provided both a profound insight into the nature of the universe and a powerful new method for measuring cosmic distances. The profound insight was that the universe is expanding. If every distant galaxy appears to be rushing away from us, and if the recession speed increases with distance, this does not mean we occupy a special position at the center from which everything else is fleeing. Rather, space itself is expanding uniformly, carrying galaxies along with it. Imagine a balloon with dots painted on its surface representing galaxies. As you inflate the balloon, every dot moves away from every other dot. And the farther apart two dots are, the faster they separate. This analogy captures the essence of cosmic expansion. Any observer located at any galaxy would see all other galaxies receding, with distant ones receding faster, exactly as Hubble observed. The practical application for distance measurement follows directly from Hubble's law. If you measure a galaxy's recession velocity by observing its redshift, and if you know the value of the Hubble constant, you can immediately calculate the galaxy's distance. The velocity comes from spectroscopy. Astronomers obtain a spectrum of the galaxy, typically using optical or infrared spectrographs attached to large telescopes. They identify familiar patterns of spectral lines, the Lyman series of hydrogen in the ultraviolet, the Balmer series in the visible, emission lines from ionized oxygen and other elements in star-forming regions, or absorption features from calcium and sodium in stellar atmospheres. By measuring the wavelengths at which these lines appear and comparing them to the known laboratory wavelengths of the same transitions measured in stationary sources on Earth, astronomers determine the fractional shift in wavelength, called the redshift, and denoted by the symbol Z. For relatively nearby galaxies moving at speeds much less than the speed of light, the redshift approximately equals the recession velocity divided by the speed of light. At very large redshifts, however, this simple relationship breaks down, and relativistic corrections become necessary. For the most distant galaxies observed, with redshifts exceeding 13, the lines have shifted so far that specialized infrared instruments are needed to detect them. The James Webb Space Telescope, launched in 2021, has proven particularly powerful for observing these high redshift systems, detecting galaxies and quasars as they appeared less than 500 million years after the Big Bang. Candidate galaxy UDFJ 3954628, observed with redshift near 7, appears as it existed roughly 13.2 billion years ago, when the universe was less than 6% of its current age. The Hubble constant, represented by h0, stands at the heart of using redshift to measure distance. Its value determines the proportionality between recession velocity and distance. Modern measurements place h0 near 70 kilometers per second per megaparsec, meaning a galaxy receding at 700 kilometers per second lies 10 megaparsecs away. Double the recession velocity to 1400 kilometers per second, and the distance doubles to 20 megaparsecs. Determining the Hubble constant requires measuring both the recession velocities and the distances of galaxies independently. The velocities come from spectroscopy, but the distances must come from other methods established through the cosmic distance ladder. Throughout the latter half of the 20th century, astronomers vigorously debated the value of h0, with measurements differing by factors of 2. The tension gradually resolved as improved observations, particularly from the Hubble Space Telescope, converged on values near 70 kilometers per second per megaparsec. However, interesting tensions have emerged in recent years. Local measurements using the cosmic distance ladder yield values near 73 kilometers per second per megaparsec. Measurements based on the cosmic microwave background radiation's temperature fluctuations suggest values closer to 67 kilometers per second per megaparsec. This roughly 10% discrepancy may point to subtle systematic errors in one or more methods, or it may hint at new physics not captured in current cosmological models. Additional calibration methods, including geometric distance measurements to galaxies hosting masers such as NGC 4258, provide independent checks but have not yet fully resolved the tension. Despite these debates over the precise value, redshift-based distances have proven enormously powerful for mapping the distant universe. Once a reasonable value of h0 is adopted, measuring distances to remote galaxies requires only obtaining their spectra and calculating their redshifts. This is far easier than detecting other distance indicators in distant galaxies. Consequently, redshift measurements have been obtained from millions of galaxies, allowing astronomers to construct three-dimensional maps of cosmic structure extending across billions of light years. These maps reveal that galaxies are not distributed randomly, but rather arranged in an intricate cosmic web of filaments, sheaths, and clusters separated by vast voids. At such extreme distances and look-back times, converting redshift into distance becomes more complicated because the universe's expansion rate has changed over cosmic history, accelerating in recent epochs due to dark energy, but decelerating earlier when matter and radiation dominated. Cosmological models must be invoked to translate redshift into proper distance measures, and different definitions of distance become relevant depending on the question being asked. Redshift-based distances carry important limitations. Unlike parallax, which provides purely geometric distance measurements requiring no assumptions about cosmology, redshift distances depend intimately on the cosmological model adopted. The conversion from redshift to distance requires not just the Hubble constant, but also the universe's matter density, dark energy density, spatial curvature, and other parameters. For relatively nearby galaxies at low redshift, these model dependencies remain small. But for distant objects at high redshift, the choice of cosmological model significantly affects the inferred distance. Another complication arises from peculiar velocities, the motions of galaxies due to gravitational attraction to nearby structures rather than the overall cosmic expansion. These peculiar velocities can reach hundreds of kilometers per second, comparable to or even exceeding the Hubble flow for nearby galaxies. A galaxy's observed redshift includes contributions both from cosmic expansion and from its peculiar velocity, making it difficult to extract a clean distance estimate for relatively nearby objects. Only at distances large enough that the Hubble flow dominates over peculiar velocities, typically beyond about 50 to 100 megaparsecs, do redshift-based distances become reliable. Nevertheless, for the vast majority of galaxies in the observable universe, redshift provides the only practical means of estimating distance. The method extends from the realm where other distance indicators become too faint to detect at a few thousand megaparsecs out to the observational horizon more than 10,000 megaparsecs away. This represents a reach more than 1,000,000 times greater than parallax and several times greater than the most powerful standard candles. Within this enormous volume of space, redshift measurements have revealed the large-scale structure of the universe, traced its expansion history, and allowed astronomers to test cosmological models against observations spanning most of cosmic time. The discovery that galaxies recede from us with speeds proportional to their distances transformed our understanding of the cosmos. What began as mysterious spectral shifts in fuzzy nebulae became the key to measuring the universe's vast scales and understanding its fundamental behavior. Redshift connects the motion of galaxies to the expansion of space itself, turning the universe's most fundamental property into a tool for measuring its vast dimensions. In learning to measure these cosmic distances, we have simultaneously learned what the universe is and how it behaves, revealing an expanding cosmos far grander than our ancestors could have imagined. From ancient shadows cast in Egyptian cities to the stretching of light across billions of years, humanity has built a cosmic distance ladder that reveals the true scale of our universe. Each rung, parallax for nearby stars, Cepheids for neighboring galaxies, Supernovae for the deep cosmos, and Redshift for the most distant reaches, builds upon the previous, creating a chain of measurements extending across incomprehensible distances. These techniques have done more than measure space. They have revealed an expanding universe dominated by mysterious dark energy, shown us galaxies as they appeared when the cosmos was young, and demonstrated that we inhabit a universe far vaster and stranger than our ancestors imagined. The methods we developed to answer the simple question, how far, have ultimately revealed what kind of universe we live in and how it evolves. Thank you for joining me on this journey through cosmic measurement.